Hi, folks, and welcome to Kindergarten Calculus. Today, we're going to be focusing on Riemann sums and the integral. This is going to be awesome. And while this might not give you the foundation and the experience of a true calculus class, I will give you enough info to be able to make it through your measly physics class. No problem. So, what is this all about? I know at this point in time, you've learned how to do derivatives. Today, we're going to learn two important things. One involves undoing derivatives, while the other involves finding the area under curves. What's incredible about this is those two ideas are actually one in the same. This is going to be awesome, and why don't we go ahead and get started? The whole idea behind Riemann sums is that we are going to be taking little bitty rectangles of area and adding them all up until we've accumulated so many rectangles that we have the full picture. I'll show you what I mean because it's a little hard to describe without pictures, of course. So here I have the graph. We're going to call this graph y equals 3. I think you can verify for yourself that this is in fact the graph of y equals 3, and it does start at x equals 0 and continues up to x equals 6. Now, if we want to find the area between the x-axis and this graph, of course, that would be extremely difficult to do. Maybe not in this case, but in some cases, it truly is. So what I want to do is I want to show you a way that it can be done. I'm not going to say easily, but it can be done. What we're going to do is we're going to create a whole bunch of little rectangles. So I want you to pretend that that's actually a rectangle, even though it clearly I can't draw. All right. So here's some more rectangles, a whole bunch of rectangles. Each of these rectangles has two very important properties: a height and a width. Of course, we all know that the area of a rectangle is its height times its width, or you can call it its base times its height, or whatever you want to call it, length times width, whatever. It's irrelevant. The important thing is that we can find those measurements for each one of these rectangles. Now, what's interesting is that the height of each rectangle is going to be wherever it hits the graph that we're looking at. Now, this particular graph is y equals 3, so that's not going to be too hard. The height of each of these rectangles will be 3. So if we take a look at our very first rectangle, this one right here that I'm kind of shading in for you right now, all right? Again, I can't draw. You know I can't draw, so I'm not even going to try to pretend. But that is pretend a rectangle anyway. It has a height of 3, and it has a width of, well, I can't really tell in this case, but what I am going to do is I'm going to call that width delta x. So this first rectangle has an area of 3 times delta x. There it is. All right, well, let's take a look at our next rectangle. Of course, if we look at our next rectangle, it also has a height of 3, and it also is going to have a width of delta x. In fact, in this rather easy example, each one of these rectangles is going to have the same area, a height of 3 and a width of delta x. So, how do I add up all of these rectangles? Well, I just count however many rectangles I have, which means I need to keep drawing and drawing and drawing. Of course, the wider the rectangles are, the easier it is, but in some cases, it does make my work a little less accurate, and I'll show you what I mean by that in a moment. But there we are. I've drawn rectangles all the way from x equals 0 all the way up to x equals 6. And what I'm going to do is I am going to sum. Now, this is the capital Greek letter sigma. Don't let that scare you. It simply means adding all of them up. What am I going to add up? Well, I'm going to add up each of these rectangles. And here's the thing. Each of these rectangles has a height represented by f of x. Now, I'm going to call it f of x sub I because each of these has a different x sub I that I'm going to use. All right. In this case, I'm using the middle of each rectangle as my x sub I. And if I go up to the function right there, is that particular f of x sub I right there. Now, x sub I could be the left side of the rectangle, in which case it would look like this for this rectangle right here. It's on the left side. X sub I could represent the right side of the rectangle, which it would be right here for this rectangle now. But you're going to see in a moment that it doesn't really matter whether I use the left or the right. The result will be the same. So this right here represents the height of each rectangle. And then, as we said, each of these rectangles has the same width. Well, not the way I drew them, but in reality, they all have the same width, which we're going to call delta x. And folks, this right here is called a Riemann sum. Maybe I should label this as the width. Clearly, I didn't practice this ahead of time, but that's okay. That's all right. All right. So this is the Riemann sum. This is going to work for any function, making rectangles out of it and adding them all up. We, in calculus anyway, call it an accumulating area. There was one rectangle, then the next one, then the next one, then the next one, and we just accumulate all of them as we go, and we end up with our full area under that curve. Pretty cool, pretty cool. But here's a question for you. What if I want more rectangles? All right, more rectangles would certainly make my result a little more accurate, depending on how many rectangles I use. So what can I do to end up with more rectangles? Well, I can't really affect the height of the rectangles. That's set by the function itself. But what I can control is how wide each rectangle is. So check this out. Maybe what I could do to try to make more rectangles is make delta x smaller. Yeah, that would result in more rectangles. But how could I get even more rectangles than that? Well, make delta x even smaller still. Now, of course, in calculus, you learned a very important concept towards the beginning of the year that will enable this to happen. What we're actually going to do is do the limit as delta x approaches 0. What do I mean by that? We don't actually want the width to be 0. If the width were 0, we wouldn't have any rectangles. That's no good. But what we can do is reduce what delta x is. And by doing that, we get many more rectangles and a much more accurate estimate to our area under the curve. This beard is getting in my mouth, so I'm going to have to do that. And that feels a lot better now, and maybe you can hear me better. We'll see how it goes. But whether I'm wearing the white beard or not, the idea is still the same, just calculating a bunch of rectangles. That's really all it is. Let me show you another example where this might work. If I clear this screen, that was kind of a boring example, but what if I do, oh, that didn't show up. There we go. What if I do this example right here? Now, this is the function y equals x squared over 3 plus 1. Now, I'm only looking at this function between x equals 1 and x equals 3. But once again, I want to know what the area is between this curve and the x-axis. How can I do that? Well, once again, I'm going to make a bunch of rectangles. And you're going to say something along the lines of, well, how can I make rectangles when the height changes? This thing is a curve. It's not the line y equals 3 like our last example. So what can I do? Well, one way is I could use the left side of each rectangle. And if I do that, I'm actually going to get a little bit of an overestimate of the true area. Well, if you don't like that, that's fine. Maybe what I could do instead is use a right rectangle. Well, that's not a very good picture at all. Anyway, if I use the right side of each rectangle, it also is not going to give me a very accurate picture. I said that the left would be an overestimate. I was wrong on that. The right ones would be an overestimate. Here's an example of a left rectangle, and clearly that is completely below the curve. But here's the fact of the matter. If we're doing the limit as the width of each rectangle approaches 0, all right, remember this is delta x, it's the width of the rectangle. As those approach 0, what we're going to see is it doesn't really matter whether we use the left or the right or even the middle. All right, we can still use this function right here, f of x sub I times delta x. Add up all those rectangles, and they're going to be so tiny on the horizontal that you're not even going to notice that these are rectangles. They're going to almost look like just line segments to you because the width of each one is tending towards 0. All right, and if we do that, what we're going to end up with is a beautiful picture. It's going to be all filled in, and even though they're all going to be rectangles, you're not going to recognize them that way. It's just going to look like it's shaded in. Of course, for this particular example, since we know what the function is, we could write our Riemann sum like this. We could write x sub I squared over 3 plus 1. That would be the height of each rectangle, and that would be the width. All right, now we have this sub I here. That's called an index. That essentially tells us which rectangle we're working with at that point. Here's a little thing I didn't tell you earlier. We're going to start with I equals 1. That's our first rectangle, all right? And we're going to go up to I being essentially infinity. For now, we're going to call it n, but in calculus, we'll learn that we're going to do n goes to infinity, all right? So how many rectangles are there? Essentially an infinite number, because each one has a width of very close to 0. And this would be our Riemann sum for this picture right here. All right, how do we evaluate that? That's not important right now. What's important right now is the concept, the idea that all we're doing is accumulating a whole bunch of increasingly small rectangles and coming up with our area under the curve. If I can find, let's see here, if I can find what I have loaded up for you. Yeah, here we go. Here's a pretty good picture of what I'm saying. This is the graph of y equals x squared. And you can see that the rectangles are getting smaller and more plentiful. And as they do that, the area under that curve, y equals x squared, becomes more and more accurate over time. What you're seeing is an animation that's visualizing that delta x is getting smaller and smaller, and tending towards 0. When the width gets smaller, we end up with more rectangles and a more accurate area. Pretty cool. All right, but that begs a question. Is there a way that we can actually just scrap these rectangles completely and just go right to the area? And the good news is, yes, there is. If I can get that loaded up here for you, I'll show you what I'm talking about. Yeah! All right, so what exactly is going on here? What's happening with Rick Astley on this little meme that I found? Well, there's the Riemann sum on top. And sure enough, you can kind of see that is Rick Astley. The pixels are kind of large because, if you have to do it by hand, they're going to be kind of large. But what we're going to do is we're going to scrap that Riemann sum and jump right down to this squiggly thing down here that we call the integral. Yes, the integral is the limit as each of those rectangles goes to 0, and we get an infinite number of them. Take a look at that Rick Astley picture on the bottom. That's clear, and that's beautiful. So, how exactly does that work? Well, I'd love to show you. And I'm going to show you by going back to our original graph which was very, very basic, just the line y equals x. And not y equals x rather, but y equals 3. All right, so here's what we're going to do. We're going to find the integral of this function, which we're going to call f of x, and where we were using where we were using delta x for the area of each rectangle. Let me just draw a rectangle here. This is what we were calling delta x, right? With integrals, an integral assumes that that limit has been done. So delta x approaches 0. And what we're going to do is we're going to call that dx. Dx is an approximation that's so tiny, it's infinitesimal. We can't even see it, but it is there. All right. So this is how you set up an integral. There's the function. This is the variable of integration, dx. And then we need to put our bounds on here. Again, we're going from x equals 0 up to x equals 6. Wow, that's a terrible drawing. Well, we'll go with it. So we're going to go from 0 up to 6. And if we evaluate this function, this will give us the area under that curve. Of course, the entire area is just a rectangle. You've already realized that. And you know that the width is 6 and the height is 3. So come on, let's face it. We all know, you, me, Miss Coats on, we all know that this area is going to end up being 18. But let me show you how to evaluate this, and I'll show you kind of an easy example of how this works. So the function that we are using in this case, the function that we're using is the function y equals 3. There it is. All right. I did mention that we were going to be talking about area under a curve, but also undoing a derivative. Well, what's cool about the integral is that is the magical mystery function that undoes the derivative. So here's the question for you. The derivative of what function would give you 3? Now think hard about that. Okay, the derivative of something gives you 3. Hopefully you realize that the function whose derivative gives you 3 is the function 3x. All right, so this integral is going to evaluate to 3x, but we do have bounds. So I'm going to put a little vertical bar here, vertical pipe, and we're going to put our bounds 0 to 6. All right, how do we evaluate from here? Well, from here it could not be easier. I take the top number and drop it in for x. 3 times 6, that's 18. Then I subtract whatever I get when I stick the bottom number in for x. That's 3 times 0, which gives me 0. And 18 minus 0, let me verify real quick. Just as I suspected. That does give us an area under the curve of 18. Pretty cool. So we found the area under the curve, and we undid a derivative all at the same time. Folks, that's pretty sweet. All right, but why don't we take a look at another example, the example that we were looking at previously, the one where it was y equals x squared over 3 plus 1. All right, so once again, we are going from x equals 1 up to x equals 3. And I wish I could draw straighter lines, but you know, it is what it is. All right. Again, this is the function y equals x squared over 3 plus 1. And so what we're going to do to figure out the area under this curve is we're going to do the integral from 1 up to 3 of the function x squared over 3 plus 1 dx. All right. Well, to do this one, we need to think hard. The derivative of what function would give us x squared over 3? Of course, when we do the derivative, remember that we always drop a power, all right? If we did the derivative of x to the n, let me write this off to the side. If we did the derivative of x to the n, remember that what we would end up with is n multiplied by x to the n minus 1. So when we do a derivative, we drop a power. Okay, so how are we going to do the integral? Well, remember, the integral undoes the derivative. So here we go. we know that if we do this, we should end up back at x to the n power. How does it work? We are literally just going to add 1 to the exponent and divide it by that same number. Check this out. It's going to look like this. We're going to go x to the n minus 1, but we're going to add 1 to that exponent. All right, of course, the n is out front, so I better keep that there. But once we do that, I'm now going to divide by whatever our new exponent is, which is that. And of course, if you clean this up a little bit, I think what you'll find, we have x. This is going to be to the nth power. On the bottom, in the denominator, we're also going to have an n, which is going to cancel out this n, taking us right back to our original function. All right, so if we want to look at this in practice, that's the theory behind it, of course. But if we want to look at it in practice, let's take a look at the actual derivative of x squared over 3 plus 1. I'm going to suggest that it's not really that bad. In fact, it's going to go like this. X squared is going to turn into x cubed. And then I'm going to divide it by a 3. Well, folks, there's already a 3 down there, so that's fine. There's the 3 that was already down there. And now I'm going to put another 3 because of that exponent. All right, so, well, we can clean that up a little bit. Let's just call it x cubed over 9. And then once again, what function has a derivative of just 1? Oh, yeah, x. Yeah, there it is. All right, and we're going to evaluate this antiderivative, if you like, from 1 to 3. So let's go ahead and try it. If we put 3 in for both of these x's, what we're going to end up with here is 3 cubed over 9. 3 cubed over 9. That's 27 over 9. That's 3 plus this other 3. That's what happens when we drop 3 in there. Now, if I go ahead and I drop 1 in there, of course, that's just going to be 1/9 plus 1. All right, so what we really have is 6 minus 1/9 plus 1. That's just going to be 10/9, I believe. Work that out, and you'll see that we're going to have an area under this curve of 44/9. Now, I could have done a million little rectangles. I certainly could have. We could have spent all the rest of whatever weekend is coming up. We could have spent all that weekend calculating the areas of all of these rectangles. And if you did it accurately, you would get something around the correct answer. But if you want the actual correct answer, it involves our friend, the integral. And that's how this all works. Isn't it crazy that the integral finds the area under the curve and also undoes the derivative? That's very interesting. It's almost like if I know the velocity of something, I could do the integral and end up with position or displacement, if you like. All right, so I'm sure you'll be talking more about that in physics class. I know that we'll be talking more about that in calc. So we'll approach that when we get there a little bit later from now. However, I also want to show you how we can do the integral of trigonometric functions. So here's a little trig function for you that I want to take a look at. All right, this is the function y equals cosine x. All right, don't freak out when you see trigonometry. It's just math. It's just stuff. All right, clearly I'm starting at 0, and it's not very clear here, but I am going up to pi over 2. Of course, the cosine of pi over 2 is 0. So really what I'm trying to find is the area of this first hump, if you will, of the cosine graph. All right, well, let's take a look. We're going to do the integral of cosine x dx, starting at 0, going up to pi over 2. All right, the hard part about this is we need to ask ourselves, the derivative of what function would give us cosine? The derivative of what function? The derivative of what function would give us cosine? Well, think hard about this one. Think hard about this one. You might want to say sine. Is that true? Is the derivative of sine equal to cosine? Yeah. It absolutely is. So when I do the integral, what we're going to do is the antiderivative, which is sine of x. We're going to evaluate that from 0 to pi over 2. Well, let's see what happens. When I drop pi over 2 in here, what is the sine of pi over 2? And of course, using your unit circle or your knowledge of whatever, that's going to be 1. Fantastic. Now let's take 0 and put that in. So what is the sine of 0? Oh, that's 0. Interesting. So the area of this region right here actually is 1. Pretty cool. Pretty cool. Now, of course, I know in physics, you tend to use degrees. That's because physics isn't quite as pure as mathematics, where we prefer superior measurement, for our angles and stuff. So I'm going to continue to use radians, but I understand in physics, you have to switch your calculator to degrees and do it using inferior methods. It is what it is. It's okay. But I'm going to continue to use radians. It's all good. Tell you what, let's do one more example. This is an example I really like because it's actually almost the same graph. The only difference this time is we're not going from 0 to pi over 2. No. We're going from 0 all the way to pi. Now, this is going to be kind of odd. I wonder what this is going to look like. If you don't want to think about it and you just want to do the integral, then okay. It's cosine x dx going from 0 to pi. Just like in our last example, the antiderivative of cosine is sine of x. And if we evaluate that from 0 to pi, well, let's see what happens. Drop the pi in there. Sine of pi, that's 0. Now, drop the 0 in there. The sine of 0 is also 0? Wait a minute here. How can the integral of this be equal to 0? How can that be the case? Well, I will be happy to show you, of course. We already found this area right here. We already found that. We know that this area is equal to 1. That was easy. That's between the x-axis and the graph. However, there's a little bit more now. If we start at the x-axis and go to the graph over here, we're actually going down. This, if you do the integral down here, what you're going to find is that this area, if you will, of course, it's not a true area, but this integral would actually be equal to -1. And so you can see that these two regions have the same area, but one is positive above the x-axis. One is negative below the x-axis. They're the same area, though. They are going to cancel out and give us a value of 0. So, kind of cool, kind of cool. All right, so just to recap, of course, we looked at Riemann sums is how we started this whole adventure. All right, and just remember that Riemann sums, we're just looking at the limit as the width of each rectangle approaches 0. And how many rectangles are there? Well, we're starting at the first rectangle and going all the way to the nth rectangle. Each rectangle has a height of f of x sub I and a width of delta x. Of course, that width is decreasing as we go, which means there's more and more and more rectangles. All right. But after we've, eliminated, not eliminated, but after we've decreased the width of those rectangles as much as we possibly can, what we're actually going to end up with, the limit as delta x approaches 0, is actually going to be the integral, right, from a to b of our function dx. Pretty cool. Now, as far as integration rules, if you are integrating a constant, let me call it k. If you are integrating a constant, of course, that's just going to give us the constant times x. I'm going to add a plus c onto this one because I'm choosing not to put bounds. If I don't know where it's starting or where it's going, I can still do the antiderivative. I just don't know how high or low that graph is going to be. So I add a plus c. Don't worry too much about that. We'll talk about that later. If I'm doing the integral of a polynomial term, let me just call it x to the n. and I screwed up. I should have put a dx here, and I definitely should put a dx here. But if I do the integral of x to the n power, I'm just going to add 1 to the exponent and then divide the entire thing by whatever my new exponent is. There we go. Finally, if I'm doing trigonometric functions, the integral of cosine of x dx, we've already said that the integral is an antiderivative. It undoes the derivative. So that would just give us sine of x plus c. And the last one, we didn't take a look at one of these examples, but if we were to do the antiderivative of sine of x, think about this. The derivative of what function would give us sine x? I know your first instinct is to say cosine, but let's think about this. If we did the derivative of cosine, what would that give us? Oh, that's actually negative sine x. I want positive sine x. So how can I make that happen? Well, I'll just put the negative on the cosine. And there you go. So folks, those are the major integrals that you're going to be starting with in physics. We will, of course, be taking a look at those in calculus as well. But that should be enough to get you started with where you're going from here. I look forward to actually developing this with you and showing you the beautiful intricacies and the experience of developing the integral. We'll be doing that in the coming days in calculus, but now you are set for physics. Thank you for joining me on this episode of Kindergarten Calculus. Folks, have a great rest of the day, and I look forward to seeing you soon. Have a good one, folks.